Hey, hi you guys. I'm having trouble with the link again, so I had to create a new link. I'm going to post it in the live video, so just bear with me just a second here. Okay, for some reason it's not letting me bring it up. But give me just a minute, I'm gonna post it in Canvas. Okay, there we go. So we will begin lecture and it will be recorded. I know there's been some confusion with the links. Let me turn on the display here. So today we're going to cover, hello Devin, I see that you are in. Thank you. I'm sorry about the trouble with the links. Eventually we'll get this all figured out, probably by the end of the semester. Okay, so let me bring up the slide here. Today we're going to be talking about Ohm's law and voltage, current, and resistance, and some information on how to measure those things. Okay, so let me adjust the camera here, make sure you guys can see these slides okay. I'm still trying to get with Mr. Foster to see if he can show me how to share my screen. So here we are again, 151 basic electricity, week 2, Wednesday. And we are going to be talking about Ohm's law. I'm going to start with Ohm's law. Okay, so Ohm's law. This is volts equals current times resistance. Okay, and it's that is the abbreviation. Remember, I stands for current, but we measure current in amps, right? Amps is our unit of measurement. Okay, and then it's written out for you there. Volts equals amps times ohms. So that would be using the units of measurement for Ohm's law. Hello, Jonathan Castillo, I see you. I posted this link in canvas, so hopefully people find their way there. Okay, so the relationship between voltage and current and the relationship between resistance and current. Voltage, if voltage goes up, current will go up. If, as far as the relationship for resistance and current, if resistance goes up, current goes down, right? If there's a resistance in our wire, the current is not going to be able to travel through as easily. Voltage, if we have more power, then the current is going to increase. Voltage and current are proportional and directly related to each other. Resistance and current are inversely related to one another. So resistance and current go the opposite way. Current and voltage are have a direct relationship. Like we said, increase in current, increase in voltage, increase in current, increase in resistance, decrease in current, right? Conventional flow, the conventional flow of electricity or conventional flow of electrons. So when we talk about conventional flow, it's going to mean that the current flows from the positive terminal of the battery or power source to the negative terminal of the battery. Conventionally, that is how it operates. Conventional flow, positive to negative. Electron flow. So electron flow is going to be the opposite flow of electrons. It's going to flow the opposite way. Current flows from the negative terminal of the battery source to the positive terminal. Okay, so we have conventional flow and electron flow. Conventional flow is our conventional flow of electrons, which flows from positive to negative. Electron flow is the opposite, flows from negative to positive. So what we're going to be doing in this class, what you guys will be doing in lab with Mr. Kimball, is you want to be able to find the current of a wire, find the current of the circuit that you may be presented with. So finding the current. Here I've written an example of a battery source of 12 volts. So we have a battery source of 12 volts. And it's connected across a 4 ohm resistor. Okay, so to find the current in a circuit, we can use Ohm's law, that formula. So Ohm's law is voltage equals current times resistance. Okay, so in our example here, we have a 12 volt battery. So that's going to be our voltage. Voltage equals 12 volts. We're looking for the current. So we have 12 equals I, and what we want to find is I. Our battery is connected across a 4 ohm resistor, so our resistance is 4. Okay, so I've written this example out for you. We have our formula. We have our example. We have our 12 volt battery. We don't know what I is. That's what we're trying to solve for. I being current. Current being measured in amps. And resistance we have is 4. We have a 4 ohm resistor. So some basic math here. Here's our 12 volt battery in our formula equals I, which we do not know, we're trying to solve for, multiplied by our 4 ohm resistor. So solve for I, we're solving for current. We're going to divide both sides by 4. Basic algebra, we want to get the variable isolated, right? So we're going to divide 4 by 4, and we're going to divide 12 by 4. So that will give us 3. So 3 amps is our current in that circuit. The current that's running through that circuit is 3 amps. And here we have it written out in form using our units of measurement, the abbreviations that they stand for, amps. Our current equals 3 amps. Okay, so this example I am going to write on the board for you because it's a little more complicated, and you guys are going to need to be able to read these circuits. I'm going to move this camera a little bit so that you guys can see the board. And I will turn on the light. Okay, so in the slide, you guys can't see it right now, but I'll put it back up there in a second. In the slide, what we're doing is I have an example where we have 3 resistors. So this is all a little bit of basic symbol identification. So the symbol for resistor is going to be like this. So this is, you guys probably can't see that. I'll try and write it bigger. Okay, so symbol for resistor. Yeah. It usually has like 3 little, okay, resistor. Let's see if you guys can. Okay, so in my example in the slide, which you will see, we have 3 resistors. Okay, resistor 1. I'm going to draw these other resistors smaller just so I can fit them on the board. Resistor 2. So how you're going to see that abbreviated is R1, resistor 1. R2, resistor 2. I drew it smaller here, but it's the same symbol. Okay, and R3, resistor 3. So we have our 3 resistors, okay? R1, R2, R3. And they are connected in series across a 60-volt battery. So what that looks like is, here's our resistors. This is our circuit. And our symbol for battery, you will see, will be something like this. You guys probably can't see that either. Let's see if I turn off the back. Okay, that didn't help, so I'm going to leave the light on. There we go. That's better. Okay, so we have resistor 1, resistor 2, resistor 3. We have our symbol for our battery. Sometimes you'll see it like this. Sometimes you'll see it with a couple more lines. So maybe like that. That is the symbol for battery when it's drawn in a schematic or a circuit. Okay, so here is our circuit with our 3 resistors, our 60-volt battery. Okay, this is my example and it's written in the slide, so you guys will be able to see that. Okay, so this means that our resistors are connected in series. Okay, it is one circuit, and these resistors are connected 1, 2, 3. We'll go over resistors and other things connected in parallel at a later time in this lecture. Not this lecture, but this week's lecture. Okay, so what we want to find is we want to find our current. So if we have 3 resistors, we have R1, R2, R3, and I'm going to tell you what the resistance of these resistors are. R1 is 5 ohms. Okay, R2 is 4 ohms. And R3 is 3 ohms. Okay, and so you guys can also, when you watch this lecture, you guys can draw along with this. You can, you know, take a separate piece of paper and draw this yourself, and you can interchange the numbers and practice stuff like this. Okay, so we have our 3 resistors, we have our 60-volt battery, and what we want to find is current. Current is I. The slides might be a little confusing because the capital I, you know, just looks like this. So keep that in mind when you are reviewing the slides. It's not a 1, it's a capital I for current. Okay, so if we take Ohm's law, which is, what's Ohm's law again? It's going to be V equals IR, right? Our voltage equals our current times our resistance. So we have our V. Our V is 60. We're looking for our I. And in a circuit like this one, when you have your resistances in series, you want to add the total resistance. How you do that is we're going to add R1 plus R2 plus R3. So simple as that, okay? So we have, remember, we have 5 ohms. Wish I had another color. We have 4 ohms and we have 3 ohms. Okay, so we're going to add 5 plus 4 plus 3. So 5 plus 4 is 9, plus 3 is 12. So we have a resistance total down here. I think that's a lowercase t. I write in all upper cases, so this is actually a lowercase t. So our resistance total is going to be 12. Okay, so we plug that into our formula. So we know our resistance, our total resistance is 12. Okay, so now we want to solve for I. That's what we're trying to find is our current. So we're going to take, we want to isolate I, basic algebra, right? So we're going to divide by 12 and divide by 12. And what does that give us? That gives us 60 divided by 12 is 5. So our current equals 5 amps. And that's how it would be written in your basic units of measurement. That's the total current for that circuit. I'm going to switch back to the slides so that you guys can see that written. And you can view the rest of the slides. This is probably a bad color to use. I don't know if you guys can really see that. I'll correct that on the slides before I post them. But under example 2, if you can't read that, it says 3 resistors. And if you saw my drawing, it says the same thing, but in words instead of in a drawing. Okay, so it says example 2, and right here it says 3 resistors, parentheses R1, R2, R3, connected in series across a 60-volt battery. Okay, and then I have the formula, which is the same exact problem I just did on the board. I have the formula right here. I gave you the resistance of the resistors. We have 5 ohms, 4 ohms, 3 ohms. Let me put the ohms there. And we want to find the current. You can write in the ohms just as well as I can. So you guys know that's ohms because resistance 3 is going to be 3 ohms. So we want to find what the current is of this circuit. Okay, so I showed you that example on the board. You can plug in different numbers and, you know, practice that, but that is what it will look like in a schematic form. That's what it looks like in using the formula. So you can practice that as you need to. And as we go along in the term, it will get more complicated. So this next slide is just another version of spelling out that formula. Okay, so step one, find the total resistance, which is what we did. R1, resistance 1 was 5 ohms. Resistance 2 was 4 ohms. Resistance 3 was 3 ohms. And that gave us a total of 12 ohms. Okay, so your resistance total right here, 12 ohms. So step 2, we can plug all of this information into our Ohm's law formula. We had a voltage of 60 batteries, and all of this information comes from the previous slide. So when you guys have the slides, you'll be able to view them together. So we have our 60 volt battery. We're looking for I, our current, and we have a total resistance of 12 ohms. And here that is plugged into Ohm's law. 60 equals I times 12. We want to find I, so we divide by 12, and we find that the current is 5 amps. Also written as I equals 5 capital A, because that is our abbreviation for amps. That's our symbol. Okay, so that's Ohm's law. What I want to show you guys now, I'm going to show you a video of electronic circuits and how to measure. It's going to give you a little overview of how to measure voltage, current, and resistance. And then that will be about it for today.
The unit for voltage is the volt. 1 volt is equal to 1 joule of electric potential energy per 1 coulomb of charge. So let's say if you have a 5 volt battery, that means that each coulomb of charge carries 5 joules of energy, or it is 5 joules per 1 coulomb of charge. And so the electrons, they have more energy when they're operating at a higher voltage. A 10 volt battery can pump 10 joules of electric potential energy to every 1 coulomb of charge. And so voltage is related to electric potential energy. Now what about current? How can we describe current? Current represents the flow of electrons. It tells you the rate at which electrons are flowing. Current is represented by the symbol I. It's equal to the charge divided by the time. The unit for current is the amp. 1 amp is equal to 1 coulomb of charge that flows per second. If you have 5 amps of current, then you have 5 coulombs of charge flowing per second. Now, when I think of current, I think of water flowing. And so water can flow very slowly, or it can flow very quickly. And so you can think of that as current. If you have a lot of water flowing at any given point, the current is high. If you have a small amount of water or trickle flowing through, then the current is low. And so electric current and the flow of water, they have some similarities in that instance. Now, the next topic we have is resistance. And when you think of resistance, what do you think of? Resistance, they can be provided in a circuit by something called, or devices called resistors. And they resist the flow of current. Resistance is measured in the units ohms, represented by the Greek symbol omega. And that's basically what you need to know about resistors. They resist the flow of current. Now, here's a question for you. Which type of wire will have more resistance? Let's say a long wire or a short wire. Well, you know that a long wire will have more resistance than a short wire because the electrons, they have a greater distance to travel through. And so longer wires have more resistance than short wires. You have a greater distance to travel to get from one part of the circuit to the other. Now, here's another question for you. Which one will have more resistance? A thin wire or a thick wire? It turns out that the thin wire has more resistance than a thick wire. And to illustrate this, resistance and current, they're inversely related. As you increase the resistance of a circuit, the current decreases. So the rate at which electrons can travel through the circuit decreases if you increase the resistance. And think of a highway with cars flowing. Think of the cars as being the electrons. In which case will the rate at which cars flow through any given point be greater? Let's say if you have a 1-lane highway, or let's say a 7-lane highway. By the way, the green part here represents resistance, not current. So just keep that in mind. In a 1-lane highway, there's not many cars that can get through. And so the current, which I'm going to highlight in red, will be low in a 1-lane highway. However, in a 7-lane highway, you can get more cars passing through at any given point in a 7-lane highway. So the current will be high, but the resistance will be low in a 7-lane highway because a lot of cars can get through. And so think of resistance as being that 1-lane highway. The cars are restricted on traveling on that highway. But in a 7-lane highway, there's not much resistance. And so you can get a lot of cars, a lot of current flowing through.
Play War Thunder now. Join millions of players across the globe in massive battles on tanks, aircraft, and helicopters. In the most expensive
Sorry, this is
ever made.
ad.
Take control.
So keep this in mind. Resistance and current, they are inversely related. Now, there is an equation that relates voltage, current, and resistance together. And this equation is known as Ohm's law. Now, let's say if the resistance is kept constant, what's going to happen to the current in a circuit if we increase the voltage? Increasing the voltage will cause an increase in current. And to illustrate this, imagine if you have, let's say, a pipe that's filled with water. And so you have water in this pipe. Now, what's going to happen if you increase the pressure on this side? So let's say on the left side, the pressure is high. And on the right side, the pressure is low. But imagine this pipe is completely filled with water. So we really don't have any space here, but it's just filled with water. If the pressure on the left side is high, then the water is going to be forced to move in one direction. It's going to flow from a region of high pressure to a region of low pressure. And the same is true with voltage. Current will flow from a region of high voltage to a region of low voltage. So let's say if the potential on the left side is 10 volts and on the right side, the potential is 2 volts. In which direction will the current flow? Well, the electric potential rather, is high on the left side and low on the right side. So the current will flow from a region of high electric potential to a region of low electric potential. By the way, current and electron flow, they're different. Let's say if the electrons are flowing in this direction, conventional current is defined as the flow of positive charge. So it's flowing in the other direction. So even though current flows from high potential to low potential, electrons, they flow from low potential to high potential. Electrons are more attracted to a positive charge as opposed to a negative charge. So they're going to flow towards the more positive side. But when dealing with current, I'm going to focus on conventional current, the flow of positive charge, even though negatively charged electrons are flowing in the circuit. Now, let me give you another picture. Let's say this is negative 12 volts on the left and negative 18 volts. Let's make it, let's make this negative 4 volts on the right. So in which direction is the current flowing? That is the flow of positive charge. Is it flowing to the right or is it flowing to the left? Feel free to pause the video and think about it. Now, which side has the high potential or which side has the low potential? On a number line, which number is greater, negative 12 or negative 4? If we draw a number line, let's say this is 0, this is 5, this would be negative 4, and negative 12 would be somewhere over here. So the value increases as you go towards the right on a number line. So therefore, negative 4 is higher on a number line than negative 12. And so current is going to flow from a region of high potential to a region of low potential. In this case, it's going to flow towards the left, towards the lower potential, which is negative 12 volts. So current flows to the more negative side or the less positive side, as in the case of this example. Here, this side is more negative, so current is going to flow in that direction. So current flows from high potential to low potential. Now, here's a question for you. Let's focus on this picture. What is the voltage across the resistor? You need to understand the difference between electric potential and voltage. Now, let's call this point A, and this point B. Now, the electric potential at point A is positive 10 volts. The electric potential at point B is 2 volts. Voltage is the difference between the electric potentials of 2 points. So it's the electric potential difference of 2 points. So the voltage across the resistor is the difference between A and B. So in that case, the voltage across that resistor, we can call it VR, is 8 volts. It's the difference between those 2 points. Now, what about the voltage across this resistor? It's also 8 volts. Now, sometimes this could be negative 8, depending on how you connect it. So let's say if you connect the positive terminal of, let's say, a meter to point A and the negative terminal to point B, it's going to read positive 8 volts. However, if you connected the negative terminal of a meter to point A and a positive terminal of the meter to point B, the current will basically be reversed in that meter. And so the voltage that it's going to read will be negative 8. So depending on the way you connect it, you can get a reading of positive 8 or negative 8. But if you want to get a positive reading, connect the positive terminal to the high potential part of the circuit and the negative terminal to the low potential part of the circuit. And then you'll get a positive reading. Now let's go back to this. So we said that if we increase the voltage in a circuit, the current will increase. And also, if you increase the resistance of a circuit, the current will decrease. So make sure you understand these statements from Ohm's law. So voltage is directly related to current, and resistance is inversely related to current. So if you double the voltage in a circuit, with everything else being the same, the current will double. If you double the resistance, the current will reduce by a factor of 2. It will be half of what it used to be. If you triple the voltage, the current will triple. If you triple the resistance, the current will be 1/3 of its original value. Now let's work on some practice problems. A 12-volt battery is connected across a 4-ohm resistor. How much current will flow in the circuit? So this is the electrical symbol of a battery. And let's draw the electrical symbol of a resistor, which looks like that. And so this is a 12-volt battery. And we have a 4-ohm resistor. Now this is the negative terminal of the battery, and this is the positive terminal. So current will flow from the positive terminal to the negative terminal. But keep in mind, the electrons are flowing in the opposite direction. Now, using Ohm's law, V is equal to IR, we can get the answer. I like using it in this form because I can easily solve for any variable that I need, just using some simple algebra. So the voltage is 12, the current in the circuit is what we're looking for, and the resistance is 4. So to get I by itself, to solve for the value of I need to divide both sides by 4. On the right side, 4 divided by 4 is 1, giving me just I. On the left side, 12 divided by 4 is 3. Thus, the current in the circuit is 3 amps. And that's the answer. Number 2, a battery is connected across a light bulb with an internal resistance of 75 ohms. Using an ammeter, the current flowing in the circuit was measured to be 120 milliamps. If you see MA, that's milliamps. What is the voltage of the battery? So feel free to pause the video and draw a circuit with the appropriate elements and then solve it. Now let's start with the battery. So here's the battery, and here is the ammeter. You can just put an A in a circle, and then let's draw the light bulb, which this is one way you can draw the light bulb. Or you can draw a light bulb like this if you want. And let's turn the light bulb on. So what is the voltage of the battery? Now the ammeter detects a current of 120 milliamps. How can we convert that to amps? Now it's important to understand that 1 amp is equal to a current of 1,000 milliamps. So to convert milliamps to amps, you need to divide by 1,000. So if
I gave you $25,000 today, what would you do? Pay 2 years off your mortgage, escape the rat race for a while, buy a new car? If you give me just 90 seconds of your time right now, I'll show you how you can
take 120 and divide by 1,000. All we need to do is take the decimal point and move it 3 spaces to the left, and that will give us a current of 0.12 amps. And so that's a quick way in which you can convert milliamps to amps. Now the resistance of the light bulb, we said it was 75 ohms. So now we have everything that we need in order to calculate the voltage of the battery. So V equals IR. So the current is 0.12, the resistance is 75, and so we just need to multiply those two. So 0.12 times 75, what we have is a 9-volt battery. So whenever you're using Ohm's law, just remember, if V is in volts, then the current has to be in amps and the resistance has to be in ohms. Let's say if the resistance was in ohms, but if you plug in milliamps instead, then this will give you millivolts. So you have to be careful when you're using different units, but just to be on the safe side, use volts for V, amps for the current, and ohms for the resistance. Number 3, a hairdryer pulls a current of 0.8 amps from a 120 volt power source. What is the internal resistance of the hairdryer? So let's go ahead and go directly to the formula. V equals IR. So we have the voltage, it's 120 volts. We have the current, 0.8 amps. And our goal is to solve for R, the internal resistance of the hairdryer. So V is 120, the current is 0.8, and let's calculate R. So to get R by itself, we just need to divide both sides by 0.8. And so 120 divided by 0.8 is 150. And so the answer is 150 ohms. And that's the resistance of the hairdryer. And so it's very simple to use Ohm's law, particularly in this format. You can easily calculate the voltage, the current, or the resistance. Now, perhaps you've seen this symbol before, maybe like a triangle or something with V on top and I and R on the bottom. So let's say if you wish to calculate R, looking at what the stuff that's left over, let's say if you put your thumb on R, you can see that the resistance is voltage divided by current. Now let's say if you block off the current, if you put your thumb on the current, you can see that the current is voltage divided by resistance. Now, if you put your thumb on, let's say, the voltage, then that tells you that voltage is current times resistance, which we could see in this form. But let's say if you divide by I, voltage divided by current is equal to resistance if you need to calculate R. Or if you need to calculate current, is voltage over resistance. So those are the other forms if you prefer to use it that way. But if you just use this formula, you can find all three just by doing a little algebra. But for those of you who don't like algebra, you may want to use this chart if it helps. I think it does help, but it all depends on you which method is easier for you. But thanks for watching.
Okay, that's all I have for you guys in lecture today. I will see you guys on, what's today? Wednesday? I'll see you guys on Monday for lecture. And you guys will see Kimball in lab tonight. Bye-bye. Thank you.